That's what really counts. So yeah, I'm Chuck Bailey, and truth be told, I am an apple farmer. I have like 40 trees, and this year I had my first apple harvest, and there were 21 apples. And the largest was like, yeah, not even the size of my fist. But anyway, it's an ongoing project. And the other thing a lot of people are pretty shocked is that I'm actually a friend of the Pleistocene. I do structural geology. I generally look at the rocks, but I am a friend of the Pleistocene. I'm really delighted to be back here in Utah. So for a number of years, I worked on the Fish Lake Plateau in central Utah. And I worked there in part because I was an undergraduate and was taken there on a field trip. And it was just eye opening. It was like there are questions about landscape and landscape evolution that could be answered right there. And these are questions that go back to Powell and Clarence Dutton and things like that. So finally, there's a big roundup there. And I've been learning things today about crazy things that happen on Friends of the Pleistocene trips. So I'm a little nervous, and this might be maybe the best hour that I have in Utah. But the other thing here at Fish Lake Plateau and in those parts that I've come to understand is that all the work that we did 10 or 15 years ago needs to be reevaluated with a critical lens because of LIDAR. And I put this out there because this will be one of the stops on this field trip. And hopefully right here, you can trace what is a pretty clear scarp that's illustrated with this sort of 1 meter topography data. Well, these were faults that we were trying to find 15 years ago in the Aspens, and they were very difficult, if not impossible, to locate. But sure enough, there is evidence for fault offset on lateral moraines and things like that. So this is a region that is really very cool, and I'm excited to sort of go get reacquainted with, yeah, some of my new friends from the Friends of the Pleistocene. So that's where I'm headed. But a lot of my career has been spent trying to understand sheared rocks. So this is a pretty simple image here of a granitic rock from the Blue Ridge, kind of in its state as an igneous rock, and what can happen to it if it's transformed into a myelinitic rock. And I hope here you can see that there is a well-developed fabric. There are mineral grains in here that are highly elongated. And so understanding those processes and effectively the what and the why has been sort of the bread and butter of the research that I have typically done. And it turns out that there are things in shear zones and fault zones that are, I think, important to understand if we want to think about material flow in the crust. And to walk you through this very quickly, which is not exactly what this talk is about, imagine you have a shear zone that is 1 kilometer in thickness. Depending on how those rocks were sheared, it very much impacts how much displacement you have. And the marker here would be this nice orange line, and it's been displaced in a simple shear situation a great deal. Whereas if the deformation was much more pure shear dominated, where you're shortening and you're translating less, you would end up with an almost identical looking shear zone, but very much difference in the amount of thinning of the crust and the displacement. So one of the things that we've worked really hard to understand are things like vorticity, how rocks actually flowed in 2 and 3 dimensions. And this is really one of the reasons I was originally going to go to Oman. I was going to look at rocks and try to better understand things like vorticity and strain in the rocks there, which I'll sort of explain more. But none of that relates to the talk I'm giving today, because Oman is like this geologic wonderland that keeps giving with new projects. And so I'm going to hopefully fill you in a little bit on what we've been doing over the past year there. I'm excited about getting your feedback on what we maybe have got right, what we haven't thought about, and what may be terribly wrong. So we can have that discussion when we get to that. So Oman. Oman is a country in the eastern edge of the Arabian Peninsula, and it is a crazy place geologically. It's an arid environment, so the rocks are well exposed. Culturally, it's sort of fascinating for those of us from the West, and it's been something that when I stopped sort of working in Utah, Oman was the next place I went, and I've been working there off and on for the past 10 years. But usually, geologists show up in Oman because they are interested in seeing the ophiolites. And my wife thinks that, the ophiolite and I are like best friends. And I'm not quite sure that we are, but I was interested in going to Oman to work on the ophiolite because I had never, ever actually studied rocks that came from the mantle. And that's one of the spectacular things about Oman is it has effectively the world's largest ophiolite. It's very well exposed. It's a very thick section of mantle rocks, as well as things above the oceanic moho. So we can see really the full oceanic crustal section here. So this is a place where you can go put your finger on the moho right there with peridotite on the left and some crustal gabbros that are there. So, it is worth visiting. in that capacity. There are structures that we can see on dry land that would cost a lot of money in a submersible to go see. So here are the famous pillow lavas. And, once you've seen this, you're like, whoa, this is pretty good. But there are pillow lavas that are this well exposed in lots of places in Oman. And so this is part of the, effectively, effusives that have formed on the Paleotethys ocean floor during the Cretaceous. So let me set up the scenario here for why this is sort of interesting. Here's a schematic cross-section, and Arabia is here. And I've got a dot, and that is a dot saying LS, which stands for limestone. There's a lot of limestone exposed in Oman. And then over here, I've got a dot with the letter O, and that stands for ophiolite. See, very good. This isn't that hard. And effectively, what has happened in Oman during the latter part of the Cretaceous is we translated a section of oceanic mantle and crust all the way onto the shallow marine carbonates on the edge of Arabia. And so you have this juxtaposition that is completely crazy. We just don't see this in many places. And where we do see it, it's oftentimes dismembered. So a simplified view of Oman's current structure is the ophiolite and its kindred rocks are shown here in purple. They've been thrust over shallow marine carbonates, some which are nearly the same age. And then all of that has been folded and eroded. So there are places where we can see through in a tectonic window with the ophiolite sort of sitting on top of that in tectonic contact. So the reason I went to Oman back in the day was I wanted to study the rocks along the base of that sequence. It's got to be a huge, very important, crustal lithospheric boundary to take, 7-8 kilometers of mantle and ocean section, transport it hundreds of kilometers and place it on top of rocks that, effectively were forming at the surface. So that was really what got me there. And, it has not disappointed. This is an image from a ridge where there's a newly cut sort of water gap that cuts through the ridge. There are folded Cretaceous strata here. There's ophiolite there. There's ophiolite there. And, in this one scene, you kind of get a whole sense of it being sliced through with ophiolite on the top and these shallow marine carbonates that are exposed there. And that has led to lots of cool projects. We've looked at the emplacement of the ophiolite, weird rocks that form in the ophiolite. But the project today is about the latest and greatest, and that really came out of some of the stuff we've done at William & Mary going back. So I conned my university into giving me money to go there in the first place with the idea that I will start study abroad program. So if you give me money, I'll learn enough, and we have. So over the past 8 years, we have gone not every year to Oman, but most years. And the class is called Rock Music Oman. And there are rocks. And I have a colleague, Ann Rasmussen, who is an ethnomusicologist and plays basically Middle Eastern music. So that's where we get the music part. I hope the Oman is obvious enough. And this ends up being really an intro geology class during the day. And then we're doing cultural things during the night, and we're pretty much exhausted all the time. But that has kind of paid the freight to get us there. And a lot of these students end up ultimately sort of getting co-opted to become geologists, right? So that's the way you go. So Oman is an interesting country. It came into modernity really in the last 30 years. It was completely poor until they effectively found their hydrocarbon wealth. And it has gone from sort of almost no paved roads to absolutely modern infrastructure in about a generation. It is very easy to work in Oman in the sense that the road signs are in Arabic and in English. And that's, oh yeah, I'm learning stuff. It is now, at least in the capital of Muscat, it is growing rapidly out into the suburbs. So when I first went, I was sort of intimidated, worried that it would be difficult for a gringo to be there and working. And it actually has been no problem. And it is a place that sort of geologists flock to. Oh, yeah, speaking of things in two languages here, this is Mr. Shawarma, all right? And when you go to Oman, everyone should eat shawarma. And once you've eaten shawarma for like 4 days, you'll be ready for something else. But anyway, Oman has a lot going for it, and then the geology is easy to see. The other thing that's been really cool about working in Oman is we've been able to partner with Omani students at the Sultan Qaboos University. It's effectively the national university here. And in this scene, which the camera is a little bit flipped, you can tell all the Omani students because they're serious about wearing safety vests, right? All the Americans are just sort of hanging out there smiling. The other thing that is interesting in Oman is that The university is co-educational, but you can't do field work in a co-educational setting. So there is a women's field course and a men's field course, and it's just completely mind-boggling for those of us from the West. But when the Westerners show up, they're happy to commingle, and we've had some really good sort of camaraderie that way. So let's drill down to sort of what we're going to talk about science-wise today. We're going to focus on rocks right here near the capital of Muscat. And the important things to take away from this map are the ophiolite and rocks associated with it are shown here in this sort of bright green. The interior structures, these tectonic windows, the things that underlie the ophiolite, are exposed in the Jebel Akhdar Dome and the Sahat Hatat Dome. And these are effectively the rocks that had the ophiolite emplaced on them. Some of them are shallow water carbonate rocks that are of Cretaceous age. You see many of those here. And then others are actually metamorphic rocks with a more interesting or a deeper history, if you will. But we're going to zoom right into here. And if I go back one, you'll notice this little outlier here of the green ophiolite. All right, it's all by itself in this part of Oman. And that's where we're going to head to. And this is a place where we have a variety of interesting structures that come together. So old Muscat is right there, but everything in this map from 1992 in green is the ophiolite. And this is primarily all parts of the mantle section right here. And it is separated from effectively Mesozoic and Paleozoic rocks that are in these colors here by the Wadi Kabir fault. And the Wadi Kabir fault is 10, 15 kilometer of strike length that we can see. And then the last component of the geology in this stretch is the yellowy oranges here are effectively a cover sequence of younger rocks. They're younger than the ophiolite that crop out. And the Wadi Kabir fault has sometimes been referred to as the trailing edge of the basal thrust on the ophiolite. So the idea is that the ophiolite was in place, and this may represent the sort of almost most seaward edge of that. Or maybe it's more complicated than that. I'll give you a cross-section view right now. This is a paper that we published earlier this year in the Journal of Asian Earth Sciences. And I'm delighted that I'm the number 5 author on this paper. And so in some ways, I think that gives me great liberty. If I don't like the conclusions in the paper, I can basically say, oh, it's all a load of hooey because I'm just the 5th author in all of this. So I don't have any real stake in whether the results are good or not. But I use this to give you this cross-section here. So the Wadi Kabir fault is here on the northeast. That's ophiolite. And the rocks that fault puts the ophiolite on are effectively these Arabian platforms, shallow marine rocks. And they're in turn in contact with a big crazy fold here inside the Sahat Hatat window. Some of these rocks in this window are eclogite grade. They basically have gone down a long ways and they've come back up. And then as you step out of that window, we have the classic Samiel thrust and the rest of the ophiolite that is out there. So again, presumably this piece and this piece were once contiguous during the emplacement of the ophiolite. So my favorite village in all of Oman is a place called Kontab. And if I could speak better Arabic, I would like to retire there. You can swim, you can fish, you can ride your bike, you can do a lot of things there. And what's also cool about Kontab is it very much sits close to what I would call a geological triple point. And this triple point is where we have the Paleogene sedimentary rocks, the ophiolite, and these carbonate rocks come together. And our Wadi Kabir fault is illustrated right here. And this is actually a little activity I asked my students to do in their second level sort of geology class, sort of draw this cross-section. Of course, this cross-section is now online, so it's much easier to draw if you know where you're going to go. But take a look at this section here. Here are the Paleogene sedimentary rocks sitting on top of the ophiolite. And the Wadi Kabir fault is effectively a significant normal fault. You've actually dropped the ophiolite down, relatively speaking, to these carbonate rocks. And seems pretty straightforward, nice kind of second level geology, getting a sense of this stuff there. And now I want to show you a few pictures of real rocks. Here you can see one of the Rock Music Oman classes. It must be early on because people are smiling. Sitting here with the ophiolite in the background, an unconformable contact with these sort of conglomerates of the Paleocene Jaffna formation that sit on top of that. pretty classic example of a beautiful contact to be exposed there. And then if we step out a little further, that's the village of Contab. There's basically the northern part of the Indian Ocean. And effectively what we've got here is a fairly thick package, hundreds of meters of Paleogene to Eogene sedimentary rocks. And here's from a paper by Sirik and al. 2021. So there's ophiolite that would be kind of on the foreslopes. You've got the alluvial fan facies, shore face, and then up to a carbonate ramp in these Eocene strata there. These are all rocks that overlie and bury the ophiolite. And they are also in contact with the Wadi Kabir fault. So it turns out a paper in 2021 by Sirik and others argued for these cover rocks as forming in a super detachment to rift basin transition that occurred by normal fault movement and deposition along the Wadi Kabir fault. All right, let me try that with pictures. So here's a map from that paper. Wadi Kabir fault. The carbonate rocks that are older are shown here in purple. The ophiolite is in green again. And then this sequence of rocks in here would effectively be these upper Paleocene to lower Eocene rocks. And the argument here is that these formed in a normal fault basin. And that they argue that there are actually two generations of syn depositional normal faults, and that the Wadi Kabir represents at least part of that sequence. And obviously, some of these rocks, like the ophiolite, seem to have dropped down. So that seems reasonable. But if you ride your bike around this area long enough and you look out at the scenery, you see things like this. So here's an image. The Wadi Kabir fault is in the background. Here's your Paleogene sequence. And I hope you can see this aniform right here. It's pretty well developed there. It's sitting above a fault that's been mapped by others, and it puts these rocks on a Triassic carbonate. And so the question is, does this represent some original rollover structure during basin formation, or do these actually represent contractional structures formed from shortening across that? So we have I've taken 20 minutes to basically get you to the research question. All right. And effectively, the purpose here is for us to understand the kinematics and temporal history of the Wadi Kabir and its associated faults. And if we pare it out into two simple models, one would be the model developed by Sirik and others, that these sediments were deposited in a syntectonic basin, an extensional basin associated with slip along these particular faults. So you're creating that accommodation space, and these sediments are being progressively rotated during deposition. Or does it represent a later situation where you have older structures that are being inverted in a different sort of tectonic regime, and that you are creating contractional structures and or reactivating normal faults with slip the opposite way? So those are kind of two simple in-member models, and that effectively is what we're trying to find evidence, one or the other. All right. Obviously, this has been published, and so what have we done? Well, we've tried to create a series of really detailed maps of these structures. So this is part of that terrain. And to walk you through here, the Wadi Kabir fault. And it looks like it actually truncates this Marina fault, which is the very high angle to it. Everything that is in the yellowy orange, this represents the cover sequence. The light green color here represent rocks of the metamorphic soul. And the metamorphic soul is something that got a cool name. And I will tell you more about that. But the reason this is significant, in all the years of people working here, no one had ever mapped any metamorphic soul here or here. And typically the metamorphic soul, when we see it in Oman, occurs at the base of the ophiolite. So let me jump to that in a minute. Just wanted to put some structures on here and zoom in a little more closely here. So the cover sequence, the blue rocks represent older autochthonous carbonate rocks, and then this here represents metamorphic soul. So that anticline that I showed you in earlier picture is represented right there. This would actually be the Marina fault. You see that structure is dipping to the northeast. But the metamorphic soul is intriguing for a lot of reasons. Oh, come on, I got to click again. Yeah, take a look at this image. So here are some of my research students. And if you don't look at them, But you look at this, I mean, look at that exposure. That's a road cut in Oman. Like, we need to go through a mountain, let's just do it. And everything here is metamorphic soil, effectively low-grade metamorphic rocks. And then on top of that is this very marly marine limestone of Eocene age. Certainly looks like there may have been some dissolution and some other weird business that's happened along that contact. But this contact looks, and if you get up close to it, it pretty clearly is an unconformity there. So the metamorphic soil, if you haven't understood or heard about it before, the metamorphic soil typically in Oman occurs at the very base of the ophiolite. And so if this is the ophiolite, and this is an image from Cyril 2007 and Cowan, here's the ophiolite. At the very bottom of this, in the major fault zone that emplaces this on the other sediments, you end up with a sequence of metamorphic rocks. So if we blow that up, what we end up with in the metamorphic soil are things like amphibolites and green schists and marbles and phyllites. And so it's called a metamorphic soil because the idea is that you took hot mantle material, you tectonically emplaced it on top of effectively oceanic materials, either basalts or seafloor sediments, and that was like a hot iron which metamorphosed these rocks from above. And the other cool thing about the metamorphic soil, if you're really into it, is that you should have an inverted metamorphic gradient, where the highest grade rocks, and in places there are granulites, are at the top, and then the green schists are at the bottom. And the idea being that this was sort of the soil plastered on at the very bottom. So we found this for the first time in this sequence. We don't have any age dates on exactly when that metamorphism occurred along the Wadi Kabir fault, but it's exciting nonetheless. And this is another reason, especially if you're not an old hack, I would say there is reason to go to the field and question like everything you've ever seen on a map, because I mean, all the regional maps showed nothing like this there. And when we stumbled on it, we were like incredulous. All right. But in an excited kind of way. Okay. So we all know about the metamorphic soil right now. The rocks are well foliated and they tell probably a story in part of the emplacement of the ophiolite. But let's sort of jump back out to some other features that are in this very small area here. I want to introduce these little dots here with the big red L. And that stands for Listwaenite. We have a Listwaenite expert in the room. Listwaenite is a very complicated rock. In fact, we can't even agree how to spell it. All right, it is that contentious. But what Listwaenite is, it's a bright orange-red rock, and it is effectively a fully carbonated peridotite. You've taken the peridotite mineral assemblage, and you basically turned it into magnesite, dolomite, quartz, and iron oxides. So it is a cool rock. It's a curious rock. And another way to think about it, I think, is to think about the chemical changes that had to happen. We see this Listwaenite in a few locations directly along the Wadi Kabir fault. All right. So the only place we find it here is right in this fault zone. And there's sort of individual outcrops and little dikelets of it. But this is why it's a cool rock, in spite of the fact that it's sort of putting gray hair on my head. If you take a general garden variety peridotite and you just think about it in oxide chemistry, you've got SiO2, you've got a lot of magnesium oxide, some iron oxide, and then all the other stuff is there. So that's your box. So what is the big deal when you go from this to this? What has changed? Well, what you've done is you basically added a lot of carbon to this rock. I mean, approximately a third of it during the carbonation process. So, you know, you can let your mind run to sort of geoengineering and other things like this. But presumably, this is a natural process that has happened in and along these fault zones. So the Wadi Kabir fault does, in fact, have little bits of Listwaenite associated with it. And that makes sense because it is in contact with peridotite from the ophiolite. All right. This is about to get very exciting. This is another picture of the Triassic carbonates, the folded sequence that is in that one viewscape. And the reason it's getting excited is this is the first stereogram of it. Right? So if you are excited about stereograms, you know, this might wake you back up. So what I'm actually plotting here are poles to bedding in the Cenozoic cover sequence. All right. And you can see the layers here on the back limb, and this looks like a much steeper forelimb here. And they form a reasonably good girdle pattern. So what that is led us to say, well, okay, well then which way are these folds actually plunging? In this instance, if you take sort of the structures in the viewscape there, we would end up with a fairly gently plunging fold towards the northeast on top of this particular fault. So let's talk a little more about the faults. If you're in the field and you get up close and personal with these things, there are lots and lots of sort of mesoscale brittle structures you can see in outcrop. All right, polished surfaces, slick-sided surfaces. So I am standing looking up, kind of an overhanging face here, and nod your head if you can see the slicken lines in there. All right, that's good. That's good. And so it's the underside of a fault surface. This is in the cover sequence. The fault is dipping to the northwest. The slicken lines are approximately down dip. And this is recording actually reverse slip. So hanging wall is moving up relative to the footwall. And from that, you can create your classic beach ball diagram, right? And the beach ball diagram should make seismologists and structural geologists happy. And from that, we ought to be able to think a little bit more about, overall shortening directions associated with that. So that's one observation. Let's combine that with more observations. And what we infer along a suite of things, both in the footwall as well as along the contact, is all of these are giving us pretty much a consistent kinematic story. All right, and that's a kinematic story which is consistent with sort of shortening from northwest to southeast here across this. So I would argue that that is evidence that supports the idea of reactivation and contraction on the structure. If we slide over here along the Wadi Kabir fault, we end up with things like this. And that's a very different kind of kinematics, which suggests that along this structure, we probably have some sort of left lateral slip that is being accommodated in those structures there. So that's cool. We've got a set of interesting structures. Oh, none of these look like they are normal faults as far as the mesoscale kinematic evidence on the ground. Other things that we find, this is off to this corner right here, a little bit of metamorphic soil. And in here, we end up with metamorphic soil. And I realize that this contact should also be a thicker line right there. Cover sequence, if you get up close and personal with this, there is gouge in here. And the kinematic indicators are consistent with it being top to the southwest, reverse fault. There are more arrows to come, all right, in the talk. So we're not done with that yet, but we're moving along. So our model for this little tiny part of the Wadi Kabir fault is, I think what we have is that this was an original structure there. And we had these fairly massive older carbonate rocks, which were sitting in the footwall. And that they accommodated this northwest southeast directed shortening by effectively sitting there doing nothing. The cover rocks above them actually were buckled and folded, and there was inversion along that particular. So that's where the buttressing comes along. The idea is that there's a pre-existing boundary that you have, and that the rocks that are adjacent to it are effectively being, they're either going to slide back up it or they're going to buckle in that regard. So I would argue this structure looks something like it was buttressing and you were deforming primarily the cover rocks. And then along the Wadi Kabir fault with that same motion field, you're going to end up reactivating this here with some element of what is dextral transpression across it. So it's shortening and sliding along there. So that's our kinematic story from this small area. So now for something slightly different. Whenever I travel, I have to go shilling for GSA. All right, that's part of my job. I got to make a pitch every now and again. And so here is my pitch to the University of Utah. But I'm making this pitch with one of your famous alums. This is Anka Friedrich. How many of you know Anka? She was in the house like not so long ago, yeah? Yeah, and I was in the field with Anka and her students from the University of Munich in Oman in February. And Anka has been a great friend of mine for a long time. It is fabulous to go to the field with her, and I got to go on a field trip when I was in Munich earlier this year. But I put this slide in here because, one, I always borrow field gear from Anka when I come to the Southwest. And my understanding is it has been relocated to Salt Lake City. So you may have to see me more, all right? But the other reason I put this up here is Anka and I are working very hard to raise money to start a GSA international student field trip. And the idea is that every year we would have enough money in the bank where we could take, I don't know, a half dozen Americans and a half dozen international students to, say, Oman and do a field trip for a week, week and a half. And then in the fall, during the GSA Connects meeting, bring that same cohort back together for a second field trip here in the United States. And so that is one of the things that I have, I've spent a lot of time on the road because I think that's a hugely important thing. And so my shilling to all of you who are students is that GSA needs you, and GSA certainly is trying to create programs that would have value for young scholars, all right? And, it will probably start incrementally, and this trip that I was on with Unca, and they came to my field area, vice versa, we think it's kind of the embryonic part of doing that. So stay tuned and be a part of GSA. Okay, so voila, we got that out of the way. I would now like to move to one other aspect of this Wadi Kabir question. And this is a zoomed in version from the CIRIC paper in 2021. And try to reacquaint you with things on here. Ophiolite is in green. Cover sequence rocks are shown here in orangey yellow. And then the footwall rocks, these other carbonates, are in the light sort of purpley colors. But I want to draw your attention to this structure right here. It effectively looks like a clippa, all right? It is interpreted to have a tectonic contact with these younger cover rocks sitting on top of these older carbonate rocks. And this is actually been named by CIRIC and others as the Banurama detachment. And there's an interesting cultural story here. You can see this by going up to look at a panoramic overlook. And everyone says, oh, go to the panorama. But it turns out in Arabic, the letter P, that P sound is not actually actuated. Does that make sense? And oftentimes when native Arabic speakers are saying the word P in the English language, it comes out as B. So the Norwegians had the Omanis take them to the overlook, and they heard it to be Bananarama. And so we have the Bananarama detachment, which they argue is a low-angle detachment fault, a lot like we might see in the Southwest United States, that initiated the basin formation for all the cover sequence there, all right? And so this should be a very intriguing structure. And so their vision of this in 3 dimensions, and I always love cross-sections like this that have that there, right? You draw it the way you want it, you're all good to go. But let's walk through this for a moment here. This would be the clippa. And then you have the main surface of the Wadi Kabir fault, and they're illustrating that with a normal shear sense kinematic. They argue there's a small rider block that's sort of pasted on there. And then, if you're following this, this is our detachment fault. Yeah. And they're interpreting the detachment fault to be somewhere buried in the subsurface in the hanging wall there. And so this is part of their model of a twofold basin extension. Shallowly dipping, high magnitude slip detachment faults that were later cut by steeper normal faults, which also facilitated basin formation and accommodation space. So I have a few field pictures, and then I'm going to kind of bust out to what we are now thinking about this. So here's a photograph from up on the high ground, and the detachment fault is right here. All of these are Eocene to Paleogene carbonate rocks, and I tried to fill in their dip angles. And then everything below are Triassic carbonates, and they're all effectively dipping at a moderate angle to the north. So this is pretty clearly a tectonic contact. You've got a discontinuity above and below. And according to the interpretation of CIRIC and others, this would have been slipping towards the north. And you get that from that last cross section. So voila. Well, let's get up close and personal with that contact. Here is an up close and personal picture of the contact. That is a kind of standard size pencil. And what you're looking at in here, I hope you can maybe see, and from where I'm standing, I can't see it at all. So I'm hoping it's a better view back there, that there are shear bands in what is sort of their zones of gouge, and there are also bits of breccia in here. And these rocks are really strongly sheared, and it's even better when you add the shear sense to it, right? And they are sheared in a top to the south fashion. And that's actually the opposite kinematic from what is interpreted for this being a detachment, opening things to the northwest. So I found that to be very curious. And the other thing that's very curious, in this fault zone, there are lots and lots of voids in what are brecciated carbonates. And in these void spaces, you end up making these crazy splays of calcite crystals that are growing in the voids there. And so this is a fault zone where you've got brecciated rocks, you have holes in the rock, and then you have some kind of mineralization, probably secondary. But it is a very distinctive fault zone. And I would argue it's a fault zone that looks very near surface as far as the features that are developed there. And then let's shift to another location. What I'd like to do now is we're going to zoom right here on the Wadi Kabir fault itself, really pretty much right where this cross-section was drawn. And once again, if you look a little closely here, you've got strongly foliated rocks, you have shear bands, and these record a top to the south reverse sense of shear. And that's exactly the opposite of what has been recorded in this schematic model by Sirik and others. So all of the kinematic indicators that we see near the Klippa are providing evidence of top to the south or reverse slip movement rather than extensional movement. Yeah, and so just to put it into kind of a simple-minded model here, what I think we actually have going on is that this structure, rather than being an extensional structure, is actually representing a contractional structure much more akin to a fault bin fold, where you've taken materials, you've moved them up over a ramp, you've brought them out onto a flat, and maybe that flat was even the Earth's surface, and you've created this fault bin fold in the process. The kinematics certainly support material transport to the left, which would be to the south in this instance. So, some words. Everything we see here indicates south-directed tectonic transport and inversion of slip along this ramp. We end up with some kind of an interesting fault bin fold geometry. And, you know, it would be cool if literally that was emerging out onto the landscape at some point. So everywhere we have looked, we are not finding solid evidence for syntectonic normal faulting in the Wadi Kabir structure. So I'm going to wrap this into a time model, and then I'm going to give you my conclusions, and we can talk about this. So here's a time graph going back to the beginning of the Cenozoic. The cover sequence, and again, the names don't necessarily matter. These were effectively deposited between the late Paleocene up into the Eocene. And we go from terrestrial shore face, very coarse-grained conglomerates that are unconformably on the ophiolite to a very nice carbonate sequence, which has been inferred to be a carbonate ramp. And again, this is very fossiliferous, so the biostratigraphy is presumably pretty good. And I think that it is quite reasonable that there was north-directed extensional or normal faulting that was helping to accommodate the basin formation. So it makes perfect sense to me that there were active faults that were extending, making the accommodation space for these. In fact, in that paper that came out earlier this year, we dated gouge from the Wadi Kabir fault. And it's using sort of old school potassium argon dating of the illite fraction in these gouge zones. And lo and behold, at least one of the samples yielded a nice age, which is consistent with deposition and gouge formation at about the same time. There were a lot of other samples that we didn't put in the paper, which gave us ages that are much harder to interpret. But boom. But I think that the structures that I've outlined for you today, that we've seen on the ground, the kinematics that you see, all of that very much requires a later episode of southwest directed contraction. And I think you can put that in with a dash of transpression. You had fault zones that were effectively inverted and reactivated. And we actually have harder time constraining exactly the timing on that. It clearly has to be sort of post-seed formation, but some have speculated this might get even into the Miocene. But what we are lacking are good structures that have datable materials associated with them. And potentially carbonate age dating on the right structures may provide a tighter control on this. So that is sort of the timeline. So now how about some conclusions, and then we can wrap this up. So I hope I've left you with the impression that the Wadi Kabir fault is this curious and intriguing structure in northern Oman, and it is most likely a very long-lived structure. It may well have played a role in the emplacement of the ophiolite during the Cretaceous, but clearly it has allowed basin formation as we move towards the Cenozoic, and it has been reactivated post that basin development as well. So yeah, this reactivation have to happen after the Eocene seed formation, and there's a little bit of everything for the structural geologist, right? We've got contraction, dextral transpression, if you think about pre-existing structures. There's footwall buttressing, all right? And that, and then the last I would argue is that I think that some of the published models for basin formation absolutely need to be re-examined. Is that a delicate way to say it? Re-examined based on the structures that we actually see on the ground. So with that, I will stop and happily take questions. Thanks for your attention. Yeah.
So you mentioned the beginning of this wondering whether
let's get to the map you want. This one?
So here's my question is southwest and
Mm-hmm.
that
Yeah. Okay. Okay. So Wadi. Yep.
So between the left and the right, I was wondering whether this north southwest boundary.
It may well be, and one of the things that is left entirely without context here, other than that, is so this is the basal contact on the ophiolite, and I went there to study that contact. Why? Really great, important thrust fault. It turns out when you are on the ground, especially in regions like this, all of the kinematics that you see along this boundary are extensional, and some of my Omani colleagues have renamed some of these structures as like the northern boundary fault. And so there is extension that we see along structures like this. This could well be a tear fault. And for instance, along this structure here, there is clearly strike slip movement as well. So on a map like this, I'm not doing a good job of giving you the kinematics on these. The original interpretation is that at some point would have approximately been the fault, the thrust fault that emplaced the ophiolite. But we know that this is a dome because the rocks have been post-ophiolite emplacement folded. And not only had they been folded, then material was effectively sliding off of it at a later date. Does that help?
Yep, so then
well, I think what the case I would make, and I probably need to put a better graphic visually together, is that I think that this structure has been most likely a contractional structure in the Cretaceous. I completely think that the geometry requires normal fault movement at some point to accommodate these cover sediments, and then post that, Miocene or younger, we have. That's correct. And so the idea is that this is now an inherited structure, and whatever the far field stresses are doing, that's being modulated across that. But the latest event is actually basin inversion and contraction. Yep. All right, there. It is. Yeah. So I think for full disclosure, we attempted to date 7 or 8 gouges. And this is using an old technique, which is a new technique now. And we had sort of 3 interpretable ages. And the other ages were widely dispersed and no one likes to look at them. And we actually had ages of 90 million, 58, and like 33. Everybody's a winner, Pete. Everybody's a winner. And so I think if, in aggregate, you could make the argument that the potassium argon gouge ages suggest potentially a long-lived history of making gouge. The youngest deformation that we see that is contractional, I think it is relating to a broader Asian plate rotation relative to sort of a fixed Arabia. And so it's rotating about an Euler pole, which is just enough to provide a certain amount of shortening across the northern Arabian margin.
Oh,
uh-huh. Right. Yep, the Tethys is exactly it closed, but it opened and then it, well, yeah. And I think, yeah, good. All right, other questions? Yeah. Mm-hmm. Yep. Yep. Let me find the right slide. Aha, this is where we kind of have to have our, I'm going the wrong way. I'm sorry. Yeah, this is it. So if I really want to see what I'm doing here, I need to wear my reading glasses that I got for Christmas. But all my students make fun of me for these because they're like Benjamin Franklin readers. So I've been trying not to use them. But okay, so this is what I think we need to envision here. Oh, all right. We tell it we're recording. I want the big screen. All right, we'll deal with the small screen here. The ophiolite is there. Okay. And so what I think is that beneath the cover rocks here, in the subsurface, if you were to drill a hole, you would basically have ophiolite on top of those rocks. But we don't see that contact exposed in this study area. Does that make sense? So what I probably should do for you, and I do have them, I just don't have them in a talk, is if I showed you a cross section from the northwest to southeast, you would see this fault, you would see metamorphic soil, and then as you got further this way, it would be ophiolite on the metamorphic soil with the cover rocks entirely lying on top of it. Does that make sense? So one of the other steps that we really need to do is turn this into a three-dimensional block model. So you can see kind of, you're looking down, but you would really like to sort of see what does that geometry look like in 3 dimensions, because you got fault going this way, a fault going that way, and then there has to be a contact between the ophiolite on top and its metamorphic soil on the block. So, so that we see metamorphic soil all the way to there. So my suspicion is, it's got to be between there and there in the subsurface. They are all contractional, yeah. But this is why research never gets old. People have actually done a fair bit of effectively argon dating the metamorphic minerals in the metamorphic soil along the ophiolite proper, like where it normally is. No one has ever looked at the age of these, and so that's another project to do. Most of the metamorphic soil ages are like 95 to 100 million. Is that approximately right? Yeah. Anyway, so what if these don't end up being that age, right? But the prediction would be they probably would be at similar age. Yeah, one Carl.
Comments on some. One is like this was very interesting because when we were doing the Oman drilling, one of the questions was whatever we drill in the metamorphic soil, it's gonna be the source of the carbon of the CO2 that formed the Listwaenite. Right? Mm-hmm. Then you think about it, you have who knows how much movement of that fault of whatever you're drilling was not necessarily there, probably was not there, and this is very consistent with that.
Mm-hmm. Yeah.
And the other one, you have these massive tectonic contracts. There's any change in stresses will change the movement. The path of least resistance.
Right.
So seeing it in the small area compared to the larger picture.
Exactly. And so I think that to that point, this Wadi Kabir fault, it probably was a big normal fault at one time, and it had a fair bit of structural relief on it. And the rocks in the footwall are, they're really massive carbonates, and under shallow surface conditions, they're just sitting there. And so all the monkey business continues to happen along that boundary.
And the other one is, I don't know if it was a discussion with you or someone else, that like there starts to be interpretation that this small block of ophiolite in Muscat, it's not associated with the big block on the.
That's right.
On the southwest.
All right. So Uwe Ring has looked at, if you continue further to the northeast, there's a melange, and he's actually got new rubidium strontium ages on it, which are older than what you would expect for the classic Samal ophiolite. So if Uwe was here today, he would say this could well be a forerunner to the big ophiolite. I think that's less romantic than it's a chopped off block of the original. But I think that remains to be seen. And that's why actually getting ages on the metamorphic soil, I think, would be important. Yeah, okay.
Students, it seems like you've got a lot of students.
Yeah, I think that the study abroad program that we do, they're generally sophomores and juniors who go. Some have had 2 or 3 geology classes, and some have had 0. Some get recruited to become geologists by going on this trip. But most of the students that I've been with in Oman, they have come with me maybe twice. So they get kind of 2 chances at field work. And in one of the pictures, Aaron, big floppy hat, this was their study area. And they have just started at the University of Alberta to do planetary geoscience in that capacity. So the students who've worked with me, and I probably have had a dozen who've worked on real projects in Oman, many of them, I'd say 8 or 9 have gone on to grad school. One I'm hoping to have dinner with because they work in Salt Lake City and are not a geoscientist. And another one who worked in Oman. Oh, Lauren, that's and then another one's a very successful real estate broker in Seattle. And I'm not sure that the Oman experience sort of created that, but it's a pretty high yield in that capacity. But I would say the other thing is that with all the non-geology students who go on this trip, some of them really take to it, and then some of them are like, come on, this is too much. And so, it is a very much sort of, not everyone is in the club of being as excited. Yeah. They are. And when we are in country for this trip, it's right during their winter break. So the timing's pretty rotten. Except they also have field courses because field work in January in Oman is good. In summer, bad.
Starting March.
Yeah, and starting in March can be rotten. And what we end up with are, we actually get to see the best, female-bodied students because they're very excited about it. But the number of them that actually go on for sort of graduate education is really small. One of the things that happens in Oman is that there are a lot of, I would say, government jobs that are out there, and people with a bachelor's degree are going into those. And so one of the disconnects I have, and this is where we don't have a graduate program in geology, right? They all say, we'd love to come work with you. It's like, well, that's great, but how many of them are going abroad? And I think the number is quite small. I would basically say it's the oxides. Yeah, well, we got a geochemist. In some ways,
So it's mostly CO2. We don't really know. Like, the fluids are very different from the normal fluids, and the temperatures are low enough that you do thermodynamics, you'll expect to have, for example, graphite toxicity with hematite. Very kind of different bullets and looks. Mostly hematite.
But it's the grain size is very small. So we were whining about the petrography of Listwaenite earlier today, that it's not like any other rocks I've looked at. And then the other thing is that the rock still has 30% SiO2, you know, in oxide form. And, you know, you just don't see big blobs of quartz or some other silicate in it, but it's in there.
But they're very niche rocks, like they don't occur very often.
Yeah, exactly. That's how we need to brand it. Very niche. All right. Thanks for being here.